All right, so to recap what we talked about in our last video, all right, common ion solutions are going to be solutions which share an ion. Buffer solutions are going to be common ion solutions that are going to resist changes in pH even when we add a little bit of acid or base to that solution, okay? We're going to have two different types of buffer solutions, one which is made with a weak acid and its conjugate base ion, or we will have a weak base and its conjugate acid ion, okay? Now, to find the pH of a buffer solution before adding some additional acid or base, okay, we showed you a couple of steps last time. The first was to write our initial concentrations that we had for the solution. Then we were going to set up an ice table, all right? We were going to solve our Ka expression and get our equilibrium concentration of H+. Then we were going to calculate our pH using that equilibrium concentration of the H+ ion. Now, this is going to be just like what we did before last week, except now we're going to add a little bit of conjugate acid or base at the start in our ice table in that initial row, okay, just like the example I did yesterday, or in our last video, excuse me. Now, continuing to slide 6, now that was before we added any extra acid or base into that buffer solution. Now, what happens if we do add a little bit of acid or base to a buffer? Well, if we take a little bit of base and we add it to an acidic buffer, all right, the reaction will proceed until all of the H+ or OH is used up, okay? It's going to be trying to figure out the limiting reagent there, okay? And to do that, we're going to solve a BCA table, and I'll show you how to do that in a minute. Then, once we've solved our BCA table, the last row in that is what we're going to use as our first step to solve the equilibrium using an ice table, okay? So first, we're going to let the reaction proceed after we've added a little bit of acid and base, use it all up, and then once we've used up all of the acid or base, okay, figuring out our limiting reagent, once we've used up one of those, okay, then we're going to let it shift back into equilibrium, okay, to reestablish that equilibrium because we know that that Ka is going to push us back, okay? Now, to go through an example of this, all right, let's say that we add 0.1 moles of sodium hydroxide to that 1 liter buffer solution that we made last time with our 0.5 molar acetic acid and 0.85 sodium acetate. All right, 0.85 molar sodium acetate. All right, now, our very first step, okay, is to do our stoichiometry. Okay, and I'm going to call this the stoichiometry part. Some people call this the stoichiometry part, and then some people call this second step the equilibrium part. Okay? Now, our first part is to solve our stoichiometry. Okay? And the way that we do that is we are going to, I'm going to do that in a Roman numeral 1. Step 1 is going to be to convert everything into moles. Okay? And the reason that we need it in moles is because a BCA table is done with moles. Okay? Remember that our ice table was molarity? The BCA table is moles. They're not the same. So make sure that you use moles for the BCA and molarity for the ice table. All right? So we're going to take our 0.01 moles of sodium hydroxide. So 0.010 moles of sodium hydroxide. Is that already in moles? The answer is yes. So we are good with that one. All right. We also have 0.50 molar solution, okay? And we have a liter of that buffer, okay? So we have 0.05 molar. Molar is moles per 1 liter. We have the 1 liter of solution. So that's going to give us 0.85 moles of our HA. Okay, and I'm using HA to represent my weak acetic acid. Okay. Then, so that's our moles of acetic acid. We also have 0.85 moles per liter, because we have molarity, moles per liter of the sodium acetate. Well, the sodium acetate is basically Na and then our acetate ion. Okay, well our acetate ion is our conjugate base of our acetic acid, which is a weak acid. Okay, so then we have 0.85 moles per liter. We multiply that by the 1 liter and we get 0.85 moles of our acetate ion. Okay, again, when we make a buffer solution, we need to have a weak, either acid or base, and its conjugate. So in this case, this is the weak acid, and the sodium acetate is our conjugate base ion. Okay, now, once we have our moles for our BCA table, we're going to set up the BCA table. Okay, so set up and it's called a before and after table. And you'll see why I call it a BCA table in a second. So for your before and after table, all right, we're going to write our reaction, okay, and we're adding base to our buffer, okay. So we had OH minus, that's our base. We're adding that to our acetic acid, and it will give us H2O and our acetate ion. Okay? So again, make sure you write down your reaction. And we're going to assume for our before and after table that we're completely reacting the base with our weak acid and giving us our final product. So the very first thing we do is we put our initial, or in this case, our before row. Okay? That's why it's called the B. Okay? Then we're going to put in our change. That's where the C comes from. And then we're going to put in our after. That's where our A comes from. Now remember, H2O doesn't participate in our Ka expressions. So I'm just going to put an X through that column because I know it's not going to be used in the Ka. Okay? Now, then I'm going to put in my moles of each of my before components. Okay? I have that should be a 0. This is a 0.5. Right? The 0.5 times 1, that should be 0.5 moles, right? So of the HA, 0.50 moles of the HA. For our OH, okay, we had the 0.010 moles of the OH because it's a 1 mole of OH per mole of sodium hydroxide. Then I'm going to plug in my A minus, which is my 0.85 moles. All right. In the change row, okay, our change, that's going to be the amount of acid or base that was added to the buffer. Okay. Now, we added this amount of base to the buffer solution that we made with the acetic acid and the sodium acetate. That means that this amount of the base that was added is what we're going to use for our change. Okay? Follow your limiting reagent process. Okay? Now, we're going to remove 0.01 moles okay, because that was our limiting reagent and it was the amount of the base that was added, okay? So I'm going to remove 0.01 from each of these rows, okay? Now, the reason that we're doing that is because it's fully reacting what we're adding, and we're saying we're going to go as far as we can, okay, to push the reaction to the right. And then once we've done that, then we'll establish our equilibrium in our ice table. Okay, so we're just subtracting off our base that was added here in our change row. Once we do that, we get a 0 here because 0, we're just going to add up the 2 rows before it. So we have 0.01 minus 0.01. In the next row, we have 0.5 minus 0.01, which is 0.49 moles. And then over here, we have 0.85 minus 0.01, which gives us 0.84 moles. All right? So now that we've done our BCA, or our before and after table, okay, the next step is going to be to set up our equilibrium. Okay? So now we've done our reaction, and we assumed that it went to completion, okay, but we know that not all reactions go to completion, or there's some sort of equilibrium that's going to push us either forward or backward, depending on where we are. Okay? So, our next step, step 2, is our equilibrium step, which was our ice table. Okay? Now, we used moles as a reminder for our before and after table, and we have to do our equilibrium table with molarity. Okay? So, our first step here is going to be to get the initial concentrations using the after row from our BCA table. Okay, so we're going to use that after row, that last row. All right, and now what we're going to do is to get our concentration of HA, okay, that's going to be equal to, well, let me do our concentration of the sodium hydroxide. Our concentration of the sodium hydroxide, in this case, or our hydroxide ion, is going to be 0 moles out of our 5 liters, or sorry, out of our 1 liter for our container, which means that we have a 0 molar solution of that. Okay, so I'm not even going to worry about that right now. The next thing is going to be our concentration of HA, okay, and that's going to be the 0.49 moles divided by 1 liter, which is 0.49 molar. All right, and then we also have our concentration of A minus, right? That was our acetate ion, okay, and that was equal to 0. Oh, I'm sorry, I messed this up. But right here, what we want to do is, remember, we subtracted it from this because this was our reactants. Here, this needs to be added because it is a product. Okay, so we consumed reactants, made products, so this is 0.086. Okay, make sure that you fix that in your notes. Now, we have 0.86 moles of our acetate ion, and then what we do is we divide by our 1 liter to get our molarity, and we get 0.86 molar acetate ion in solution. Now, for the ice table, all right, what we're going to do for our ice table is it's going to be for our equilibrium reaction. All right, that means that it's the system involving that weak acid or weak base that's going to be held up in that buffer. Okay, so at this point, all right, we know that our reaction is the dissociation of our weak acid. So that's going to be HA goes to H plus, and our acetate ion. We aren't including any of our acid or base that we added because it's already been used up. Okay? We assumed that we went all the way to completion. Okay? And now we're just going to figure out the equilibrium based on what happens after that. Okay? So we have I, C, E. All right? And we're going to fill out our initial row. Our HA was 0.49. Our H plus, we don't have any information about that, so it's a 0. And our A minus is a 0.86. Notice that we have A minus concentration because of the buffer, okay? And it's a little bit different than our initial concentration would have been because we've added a little bit of base, okay? Now, at this point, we add in our change row, we take our stoichiometric coefficient, we subtract off our X for our reactants, stoichiometric coefficient plus X for products, again for the A minus. Then we add the two rows together, 0.49 minus X, X, and 0.86 plus X. Okay? Now, remember from our example yesterday that if we have a buffer, okay, we're going to drop these X's, okay, for the HA and our A minus, okay, because it's not going to change much. If you do that, you have to do your 5% rule check, but it's well worth it because having multiple X's is very, very difficult to solve. All right, now what we can do is for step 3, we're going to set up our Ka expression. Our Ka in this case is going to be equal to, because I'm dropping my X's, I'm just going to put a little red line through those so that way we know that those aren't there anymore. I'm going to put my 0.86 times my X, each to the first, and then I'm going to put that over my 0.49 to the first. Because again, I dropped that little X. Now, the Ka for acetic is equal to 1.85 times 10 to the negative fifth. Again, 1.85 times 10 to the negative fifth. So I can then solve for X, okay, which is going to be equal to 1.025 times 10 to the negative fifth, okay? I look at my table, okay, and I notice that my X corresponds to my concentration of H plus at equilibrium. Okay, because I want to solve for my concentration of H plus at equilibrium. So that way I can get my pH. So I've got this, okay? And of course I would check my 5% rule. If I do that, I get that, so 5% rule. I got 0.002%, which is less than 5%. As you can see, that's a valid assumption, so that's good. And if we do our pH, we know that pH is equal to the negative log base 10 of 1.025 times 10 to the negative fifth. Okay? When I do that, I get that my pH is equal to 4.989. After we added the base, okay? Now, the pH before, we added the sodium hydroxide, that was equal to 4.975, okay? Now notice, yes, they're different, Okay, but it really hasn't changed a whole lot from the 4.975 to the 4.985. It's basically the same, okay? Which means that our buffer did its job. It resisted the change in pH when we added a strong acid or strong base to our solution, okay? So this again is an example of how a buffer works, all right? Now, in our next video, we'll go over some new methods regarding our common ion effect and the Henderson-Hasselbalch equation.